Guys, in today's video we're going to be talking about gases. We're going to look at gases, how they compare to other states of matter, and then we're going to look at gas pressure itself and the units that we use for gas pressure. So a gas is considered a very dispersed state of matter where all the particles are very, very far apart from each other. So particles are considered infinitely far from each other. In contrast, our gases or liquids and our solids are considered condensed states of matter, meaning that all of the particles are very close to each other. So our gases, everything's very, very far apart. Our liquids and our solids, everything's very close together. So that means in our gas, things don't interact. So our particles don't interact. But in our gas, our liquid and our solid, the particles are close, so they interact with each other. Okay, and then when we think about each of these states of matter, because of how close or far things are from each other, our gases, they're very, very far away from each other, so they can be compressed. So gas particles within a gas can be compressed. So we'd say that a gas can be compressed, while our liquids and our solids cannot be compressed. So we can't really get our liquid and our solid particles any closer to each other than they already are. And then we also don't really expand in a liquid or a solid. So these don't expand. But our gases can expand. Okay. Now, when looking at a couple of other things, we can think about kinetic energy. So our solids are going to be the state of matter with the least amount of kinetic energy and the least amount of movement. So solids, very little movement. Very little kinetic energy. Our liquids move a lot. Lots of movement. And lots of kinetic energy. And then our gases have the most movement and the greatest kinetic energy of the three states of matter. And then both our liquids and our gases are going to be states of matter where the particles can flow. So particles can flow. So these are considered fluids. Right, so we have fluid movement where everything's tumbling over each other, so it's very organized. Our solid is a very organized structure. So things are not moving, they're not fluid. Okay, so let's think about what happens in each of our phases as we add or remove energy. So we're going to look at solids versus liquids and gases. So if we're going from a solid to a liquid, liquid to a gas, in order to get to each one of these phases, we have to add heat. Heat is added, increasing our kinetic energy, which allows us to move going from a solid to a liquid to a gas. In the opposite direction, if we're going from a gas to a liquid to a solid, heat is removed. So we could say going from a solid to a liquid, liquid to a gas is an endothermic process, while going from a gas to a liquid, liquid to a solid is an exothermic process. Going from a solid to a liquid, we call this melting. Liquid to a gas, evaporation. And then our solid to our gas is sublimation. Going from our gas to our liquid is condensation. Liquid to a solid is freezing. And then going from our gases to our solids is deposition. Okay, so going from our solids to our liquids to our gases, as I said, that increases our kinetic energy, so we have to increase the amount of heat. Gases themselves are going to behave in a very specific way. So we have gas properties to explain the way that gases behave. Almost always, gases are going to be composed of non-metallic elements, and they're going to have simple formulas with low molecular weights. So non-metallic are nonmetals. So very, very, very few gaseous elements, gaseous metallic elements exist without an extreme amount of heat being added in. Of course, you can always get anything to a gas if you add enough energy in, as long as it doesn't decompose. And low molecular weights allow it to actually go into the gaseous phase, right? It has to, if it's very, very heavy, it's not going to go into the gaseous phase very easily. And of course, when I'm talking about this, I'm talking about at room temperature, things that are normally gases at room temperature, not things that we had to add a lot of energy in to get to a gas. With our gases, they have similar physical properties. They're going to behave very similar to each other. And then they are unique compared to the other states of matter for a couple of reasons. They're compressible and expandable. If you have a gas, you can apply pressure and get those particles closer and closer together, essentially reducing the volume of that gas. And then they are expandable. They are going to expand to fit their container. No matter what container you put them in, they will expand until they fit that container. So they have no definite shape, no definite volume. Because the particles are infinitely far apart from each other, they have incredibly low densities, which is very different from our solids and our liquids. And all gas mixtures are going to be homogeneous. So you will only see one phase if you look at this. It'll look like one thing. So it's because they all have very similar physical properties. Here are a couple of common compounds that are gases at room temperature, and a lot of these should look familiar, such as carbon monoxide and carbon dioxide. We've got methane in here, propane, right? All of these, or all of those are ones we've talked about. We've also kind of hit on nitrogen dioxide, but ammonia, sulfur dioxide, nitrous oxide, all of these are going to be low molecular weight compounds. that don't have a lot of interaction between the particles. So when we talked about polar covalent compounds, if you look, most of these are not. Some of them are, but most of them are not. Okay, next thing I want to talk about is the idea of pressure. So when we think about pressure, it is the force applied over a given area. Okay, so the amount of force applied to an area. The greater the force or the smaller the area, the greater the pressure. And we can just look at our equation to see that. And then our force, when we talk about our force, it's the mass of an object multiplied by its acceleration. So more massive, more accelerating, more force. And when we think about a gas, we can apply this idea because when we're talking about a gas, a lot of pressure is gas pressure. So when we talk about pressure, a lot of times we're talking about gas pressure. So this is the pressure applied by a gas. So if we can get a gas to have a greater force, a greater acceleration, a greater mass, a force or a gas exerting a force over a smaller area, we can all cause gas pressure to increase. So for instance, if we get more gas particles within, say, for instance, a tire. So if we take a tire, the more gas particles we add in, the greater the pressure it is because we're applying a greater force over a smaller area because we have more and more particles. And then if we heat up a gas, heating up a gas is going to cause that acceleration to go up. It's going to cause that force to go up. So it's going to cause that pressure to go up. So heating a gas or increasing the amount of particles within a given volume, both of those will increase our pressure of our gas. We can look at gas pressure a couple of ways or measure it. So our most common one is called a manometer, which is what I've just shown below. A manometer measures the pressure of a gas. So here's a gas right here that we want to measure the pressure of. You put that gas in, you open up this, and that gas is going to apply a pressure. That pressure is going to be applied to this gray bulb or tube, which is a column of mercury. Okay, and that column of mercury will be pushed by the gas here and by the atmospheric gas. So there's going to be an open end that is open to the atmosphere, and then there's going to be a closed end that is enclosing the gas. So the gas pressure itself, our P gas, is equal to the atmospheric pressure plus our column height. So our height difference we see right here. So height difference for the mercury column. And that is going to be measured in millimeters. So gas pressure is measured in millimeters of mercury when using a barometer. So that height. We can also look at atmospheric pressure. The pressure exerted by the gas particles in the atmosphere. So we measure that using a barometer. A barometer measures our atmospheric pressure, and what a barometer is an open dish of mercury. And as the atmospheric pressure pushes down on this dish of mercury, it pushes up on this column of mercury. And then you can look at the height difference between the pool of mercury and this tube, and you could determine the pressure in millimeters of mercury. This right here, this place with no mercury, is going to be under vacuum, so there are no particles whatsoever. So nothing that's going to be exerting its own pressure against this column of mercury. So of course, when we're looking at units of pressure, the first one that should come to mind is millimeters of mercury. And that is literally what it is. It's millimeters of mercury. Now, the most common unit that we use is atmospheres. So ATM is atmospheres. But some other ones we're going to look at. Torr, which is abbreviated as, well, I guess abbreviation here is lowercase torr, and it means uppercase torr. Makes sense, right? And then we also look at PSI, which is pounds per square inch. And then PA, which is pascals. Okay, so atmospheres are the most common, and 1 atmosphere is equal to 760 millimeters of mercury. And this is an exact value. And then 1 atmosphere is also equal to 760 torr. And this is also an exact value. So hopefully you get from this that 1 millimeter of mercury is equal to 1 torr, and this is also exact. So infinite sig figs, remember. Then we could look at PSI. So 1 atmosphere is equal to 14.70 PSI. Pounds per square inch is something you would look at when you're looking at tires and stuff like that. And then pascals, 1 atmosphere is going to be equal to 1.013 times 10 to the 5 pascals. Okay, wow, that is everything for this video. We'll see you guys later. Bye.